I was inquiring, how do you get the decimals and quartiles and percentiles
Yeah, the
using
same way.
discrete?
It is okay.
Yeah.
Let's talk about it.
Yes.
So the same way you get made, so all these ones are got in the same way. For decile, remember decile is a value over 10. Let me say they want the eighth decile. Eighth decile. What do you do? It means that if here you can say let the decile be D8. D8 will be now 8 over 10, like that. That 8 over 10 is 0.8. 0.8. Now you go to the column of capital Fx and look for a value slightly greater than or equal to 0.8. If you come here, 0.1 can't, 0.3 can't, 0.6 can't, but this can. So in this case, our eighth decile is 4, like that. Let me choose now for percentile. Let me choose what? Let me say 40th percentile. Is decile okay, Arnold?
Yes, sir.
Okay. Now for percentile, let me use the word which is commonly used, middle 40% range. When they say middle 40% range, it means that that 40% must be centered in the middle. The percentage is from 0 to 100, but you are going to center the 40 in the middle. So it means that each side of the midpoint takes half, half. So this side will take half, this side will take half. Meaning this value here is 30 minus 20 to give you P, to give you 50 minus 20 to give you 30. This value here will be 50 plus 20 to give you P, 70. So in short, when they ask for middle 40% range, they want you to get P70 minus P30. Okay. Now that that is known, let's see how to get P70. P70 is 70 over 100, which is 0.7. So come to your column, look for a value slightly greater than or equal to 0.7. That value will automatically be 1 because 0.6 is smaller. So our P70 is 4. P30 is 30 over 100, which is 0.3. A value slightly greater than or equal to 0.3. We already have 0.3 here, so it corresponds to 2. That will be our P30. Then when I subtract the 2, I'll get this. So in that case, I've got the middle 40% range. So basically, that's how they get percentiles, deciles, quartiles, and medians in discrete. In discrete. Okay, is it better now?
Yes, sir. Thank you.
Okay, now we can go to continuous. Continuous random variable requires knowledge of calculus. It entirely concentrates on calculus. That's why the first bullet you saw, it says calculus required. Calculus required. So calculus I mean differentiation and integration. So the differentiation you covered in, okay, let me say pure math, and the integration you covered is much needed. Those who, was there a question? Let me first see. Okay, I thought there was a message. Mm. So those, the integration and the differentiation you covered in Math 1 is much needed in this topic. Those who looked through the items I gave you, you must have realized that there are some items you could not attempt because there are some techniques of differentiation and integration which you have not yet learned. What you covered was called differentiation 1 and integration 1. There's still more on that topic. So items which had trig functions, you could not do them. I think you saw some of them. Items which had exponentials, you could not do them. Items which had natural logarithms, you could not do them. So what you could do were items which had polynomials, because that is the only part you have covered so far in integration and differentiation. So that means that the items we're going to do, the ones which require other parts, the ones which require trig, exponentials, and natural logarithms will be skipped. We shall concentrate on the past items which require polynomials. Reason, the integration and differentiation you have covered is only on polynomials. Okay. So now that's what that was the first bullet. Requires calculus. 2, to convert from converting from small fx to capital Fx requires integration. Okay, so how do you know when to integrate? When you are given small fx and they want you to get capital Fx, you integrate. It is different here in this script where we could tabulate. Okay, but here we cannot tabulate. Continuous, if you draw a table, automatically everything is never okay. Automatically everything is never okay. So when they need to convert from capital Fx, small fx to capital Fx, you have to integrate. When they want to convert from capital Fx to small fx, you have to differentiate. Okay. And here, like we did in discrete, if you ask for mean, variance, and standard deviation, it must be got from small fx. So if a question has capital Fx and asks for mean, variance, or standard deviation, remember to convert to small fx using this expression, that for me to change from capital Fx to small fx, I have to differentiate. Okay. However, unlike for discrete, because for discrete we saw that median, deciles, quartiles, percentiles can only be got from capital Fx. Okay. When it comes to continuous, any of the two can be used to obtain those parameters. So deciles, quartiles, percentiles, median can be got from either small fx or capital Fx. So whatever you are given, you can get. For example, if I'm given capital small fx and that's for median, I don't need to first change to capital Fx. No, I can get it straight away. If I'm given capital Fx and that's for median, I don't need to first convert to this and get it. No, I can get it from here straight away. So basically, that is the brief introduction of continuous random variable. Now I want to see this, actually the whole of this, only this is a summary of the entire topic. Now next, in the items, we're going to see how to use these bullets. Okay. If there's a question you can ask before you start the items, because this is what you're going to use in the items, what I've been talking about. Okay, the silence means the introduction has been okay. Now let's start. This was item 1. Item 1 says, okay, what I'm doing, I'm trying to convert. I think some of you know that there's a topical question bank which I wrote. So what I'm doing, I'm converting those questions, UNEB questions, from old curriculum format to new curriculum format. Actually, all the questions I gave you were part of those UNEB questions. They're all UNEB questions from 2024 to 2000. Okay, so what I did, I maintained the same setting, but I had to attach some words. But this question was slightly different. This different because based on the scenario, we don't need negative values. That is why you're seeing, if you look at that question of 2024, there were some negative values, but now I removed them. So it's a little different. So that is what I'm doing. So next year, those who buy the item, the question bank, it will be scenario based. So item 1 came from UNEB 2024 question 12, and it says, a battery manufacturer is studying the lifetime of a new type of rechargeable battery. Okay. The lifetime in years of the battery is represented by a continuous random variable. So here they have specified continuous. If they don't specify, you could see this and no. Do you see these decimals? They're the ones who can tell you that it is now continuous. Okay, but the good thing they have specified for us, continuous random variable. Okay, the cumulative, do you see this word? Cumulative means we are now dealing with capital F. If you see cumulative, we are dealing with capital F. Okay, the cumulative distribution function of X behaves as follows. Bullet 1, the cumulative probability is 0 for all values of X less than or equal to 0. So Fx is equal to 0 when X is less or equal to 0. That's what that bullet means. Let's do the second one. Between 0 and 3. So from 0 to 3, between 0 and 3, the probability increases in a straight line. Do you see this word line? It means continuous. Line means continuous. From 0 at x equal to 0 to 0.7 at x equal to 3. So it means that there is a straight line. One has 0, 0, another one has 0, 0.7 in coordinate form. Between 3 and 5, the cumulative probability continues to increase linearly, that shows continuous, starting from 0.75 when x is equal to 3, reaching 1 when x is equal to 5. So from here, there's another straight line. One line is here, it stops here, then another one can come. So this is 0, 0. This is 0, 0.75. Then this one is now, this is not 0, 3. Then this one is 5, 1. Okay, let's proceed. For all values of x greater than 5, the cumulative probability remains constant at 1. So this is now a horizontal line up to where we don't know. Okay, the good thing they've told us that it is linearly. So meaning that we can use the equation of a straight line y equal to mx plus c. I think you all know from coordinate geometry 1 that given 2 points or given 2 points on a straight line, you can easily get the equation of that line. Given 2 points, you can easily get the equation of that line. So basically, that is the knowledge you're going to use to come up with the first task, because the first task says, write down the full expression of the cumulative distribution function for all possible values of the battery lifetime. Okay, so let's begin. One shall use these coordinates using 0, 0. Remember, the first one was 0, 0 up to 3, 0.75. So using those two coordinates, I can easily get the equation of a straight line by equating gradients. There are two ways of getting equation of a straight line. For me, I prefer equating gradients. Others can say, let me use y equal to mx plus c. It is still okay. It is still okay. You'll get the same, you come up with the same answer. You come up with some answer. So when I use that, I come up with this equation. Then I also go to the next coordinates, the next line, from this to this. What is the equation of that line? So I'll come and get the equation, equate gradients, then solve to get the equation of the line. So that is the equation, meaning that now I can write the full expression less than 0. In the first bullet, they told us geometric probability is 0. From this to this, they told us it's a straight line, and that straight line is given by this. That's what we have got here. From 3 to 5 is the straight line also, and that straight line we solve it and got that. That's what we write here. So in short, this y here is what represents capital Fx. This y you see is what represents capital Fx. Then they told us that all values greater than 5, the cumulative frequency remains a constant, and that is 1. That is why you see here 1. So that was task Roman 1. If there's a question on it, you can ask.
Teacher,
Mm-hmm.
I have simply not understood.
Pardon?
I've not understood what we've done. I don't know why they are lines.
Why they are lines? Continuous, it means lines. Continuous can be a line or a curve. Those are continuous values. If it is discrete, I think you saw maybe the difference I didn't put under discrete and continuous. For discrete, when they ask for a graph, they are different. They are drawn differently. For small fx, they draw vertical lines. For continuous, it is a straight line. It can be a straight line or a curve. So because they said continuous, that is why it is either linear or a curve. That's what they mean by continuous functions. What can I say? Okay, continue. For example, I don't know if you do chemistry, but in chemistry, they do what we call cooling curve, where they measure temperatures of different liquids. And when they tell you to plot, what they do, you have to draw a line through. Why? It's a curve through. Why? Because temperature is a continuous random variable. Temperature is a continuous random variable. That's why we can draw a curve or a straight line. So each time anything continuous can be represented by a curve or a straight line. I don't know if I've answered you, but still even the scenario can tell you. Let's see the scenario. The scenario tells us the word line, straight line, meaning that we have to get a equation of that line in this interval. Even here it tells you something linearly. So you have to get the equation of the straight line in that interval. I don't know that. Does that make sense?
Yes, teacher.
Okay, so anything continuous is either a line or a curve. I think along the way, as we do the items, somewhere they will tell us to sketch the curve or to sketch the PDF or sketch the CDF. You'll see that it will still be either a line or a curve. Okay. Any other inquiry on this item, part A, Roman 1? Because now after that, we shall go to Roman 2.
Teacher, excuse me.
Mm-hmm.
I'm a bit lost.
Okay.
So when we read the scenario, how to get the functions, we were finding the equation of
A
the
straight
line
line.
for both of them.
Yeah,
The different limits they had given us 0 to 3 and 3 to 5.
that is true.
Okay.
Yeah. Is it better now?
Yes.
Okay. Okay, so that is Roman 1. Roman 1. Let me just make some roll call. Kwagala Jolly, is Roman 1 okay? A Roman 1 okay?
Yes, teacher.
Okay, I'm not seeing appear. Where is appear? Okay. Then Matthew, is Roman 1 okay? Matthew,
Yeah, it
you
is.
there? Okay.
Yeah.
Okay. So now we can go to Roman 2. Roman 2 says, using your answer above, determine the probability that the battery lasts between 1 to 4. I think in the PDF I gave you, it was 1 to 2.5, but I changed it because I wanted you to understand how to answer in case the values are in different functions. Let me tell you what I'm trying to mean. From 1 to 2.5, both 1 and 2.5 are only in one function. Now, why did I change? Because I wanted you to know, what if the one value is in one function and the other is in the other function? What do you do? But still, I didn't change because it was wrong. I changed to make it a little more tricky. I only changed to make it a little more tricky. But if you want this one, we can still first do it roughly. For example, 2.5 means substitute this. Where there is x, we put there 2.5. So I'm going to put 2.5, that will be a quarter times 2.5 minus, open brackets, a quarter times 1. Then you can use a calculator. Let me see here. A quarter times 2.5 minus a quarter. It will be 3/8. So in that, if you take the question I gave you in the PDF, this should be your answer. This should be your answer. But the one I've now edited from 1 to 4, how do you do it? 1, you have to look for where those values are. 1 is in this interval. So I should use this for express this function. So when I'm getting f1, I'm going to say a quarter times 1. When I'm getting f2, 4 is between here. So when I'm getting f4, I'm going to say 1/8 in brackets 4 plus 3, like that. What I know, some of you were stopped at small fx. But here, the good thing here is that, like I've told you in the difference, for continuous, whether you're given small fx or capital Fx, you can still get the median, decile, percentile. You can also still get the probabilities. What you cannot get are the mean, variance, and standard deviation. Those ones you must first convert to small fx. So we're also going to see how to convert. I think that it was part of the question. Let me just a moment. They said from the CDF, determine the PDF. Okay. It is in the next Roman. We are going to see how to convert from capital Fx to small fx. So in short, I can either use capital Fx to get the probability, or I use small fx to get the probability. When you want to use small fx to get the probability, you must integrate. When you want to use capital Fx to get probability, you don't integrate. You simply substitute. You simply substitute. That's the difference between the two. We're also going to get probability using small fx, don't worry. But for now, let's first get it using capital Fx, where you simply substitute. Remember that. For capital Fx, getting probability, you simply substitute. If it was small fx, we could integrate from 1 to 4. But here, we simply substitute. And that would be the answer. So 4 was in this, so where there's x, we put 4. 1 was in this function, so where there's x, we put 1. Then you can get the probability they want. That is for capital Fx. Don't confuse the two. Capital Fx. If it was small fx, we're also going to do it. Don't worry. We're also going to do it. Okay, is Roman 2 okay? I know it may be disturbing you, but know that for capital Fx, you don't integrate. You simply substitute. Simply substitute. Then how do you change from capital Fx to small fx? You remember that we said you must differentiate. So do you see this? This is capital Fx. Now, to get small fx, I must differentiate each. I must differentiate each. When I differentiate 0, I get 0. When I differentiate a quarter x, I get a quarter. When I differentiate this, I get 1/8. When I differentiate 1, I get 0. Okay. Now, do you see here? This one and this one both give 0. That is why those who have already done small effects, you realize they end with something called 0 elsewhere because it contains this range and also this range. So we combine them into one and we call it 0 elsewhere. Okay. So that means that if I want to write small fx, you know what I'm going to do? When I differentiate, I'm going to differentiate a quarter x to get this. Differentiate 1 over 8 in brackets x plus 3 to get 1 over 8. Now these two are going to be combined into 1 and I call it 0 elsewhere. Like that. Others use the word otherwise. It is okay. So this one, I maintain the interval. The first one, the interval is from 0. This one, the interval is 3. So in short, that is our small fx. You simply differentiate. When given capital Fx and you want small fx, you simply differentiate. So in that small fx, we're also going to use it and see if when we integrate, we get the same value of the probability we got while using small fx. You don't need to worry. Okay, and this is a question on small fx you can ask. So what if you're making notes, know that when you convert from capital Fx to small fx, you must differentiate. You must differentiate. And two, because this first one and this last one are both 0 when you differentiate, we replace it with the word elsewhere. Elsewhere. Otherwise, if you wanted to use the inequalities, we could have written x less than 0 and x greater than 5. Like that. So those are the two ways we can write, but you shouldn't go through these complicated things. Just write elsewhere and stop. Elsewhere and stop. Okay, so let me just have it typed here. Just so differentiate, then that will be the answer. So now what I want, if one chooses to use this to get this probability, how do you do it? That's what you're going to do here. I didn't type it, but let me just handwrite it. So probability from 1 to 4 will be equal to the integral from, remember 1 is here. So it will be from 1 to 3 of a quarter. Then 4 is here. So it will be integral from 3 to 4 of what? Of 1 over 8. Like that. So if you chose to use small fx, that is what I expected you to write. Then you integrate. When I integrate a quarter, what do you think I get? Anyone to give me an answer? If I integrate a quarter, I get let me choose. Okay. Gracious, you are there? I want to integrate a quarter. Yes, if I integrate a quarter, what will I get?
X over 4.
X over 4. That is true. What about, you stay there? What about when I integrate 1 over 8? I get
X over 8.
Okay, that's good. And now you're good to go. So then from there, I'm going to substitute the limits. Where there is x, I put upper limit. So 3 over 4 minus 1 over 4. What I'm doing is just an alternative of this one is an alternative of that one. Plus 4 over 8 minus 3 over 8. Okay, then we can use the calculator. 3 over 4 minus 1 over 4, I think it is a half. Then now this one. This one to be 1 over 8, I think. 1/8. Okay. Then when we add, you realize that you get the same answer as before. So that confirms the statement I wrote that for deciles, median, quartiles, percentiles, probabilities, whether they can be got from either small fx or capital Fx. If in the question they are giving you small fx, you don't need to convert to capital Fx to get median or a probability. Just deal with it. Know that for small fx, I integrate. For small fx, I integrate. Okay. Then if in the question they're giving you capital Fx, you don't need to convert to small fx. Just know that for capital Fx, I simply substitute. Simply substitute. When you know those two differences, then you can easily work with them. So capital Fx, simply substitute. Simply substitute. For small fx, integrate. Okay, I think we are now good. We are now done with A Roman 2 and B Roman 1. Here's a question you can ask on those two. A Roman 2, we have seen both options using capital Fx and also using small fx. Then B Roman 1, you have seen that you have to differentiate if you are given capital Fx and you want to get small fx. Here's a question on those two you can ask. Okay, so the silence means it is okay. Then we can see the next Roman. Next Roman says, using your PDF, calculate the expected lifetime of the battery. Using your PDF, calculate the expected lifetime of the battery. So like I've told you, EX can only be got from small fx. So even if they didn't tell us that using your PDF, automatically you were supposed to. Because expectation, variance, and standard deviation can only be got from small fx. So I'll come and say that the formula is that. I think we saw it in the introduction part. So what I'm going to do, it means that on this fx, I must attach and multiply by x. On this one, multiply by x. So that is why you're going to see, and now it is a quarter x, because on fx, I've multiplied by x. Even here, you will see 1/8x, because on fx, I've multiplied by x. Then the limits are these ones, intervals. Limits are these ones. Then from there, I can now integrate. Now I want someone to integrate for us. A quarter x gives what? Hannah, are you there?
Yes.
A quarter x, when I integrate, what do I get?
X squared out of 8.
Okay, you stay there. What about 1/x/8? What about x/8?
X squared
Mm-hmm.
over 16.
Over 16. Okay, that's good. That's good. So in small fx, you must be confident of integration. Small fx, integrate. Capital Fx, simply substitute. Remember that. Small fx, integrate. Capital Fx, simply substitute. So I'll put the limits, then I can get the answer using a calculator. So basically, that was item 1. Item 1, if there's a question you can ask. Okay. Hope it is okay. Is it okay to proceed?
Yes.
Okay. So here, yeah. So that we have dealt with I with small capital Fx. Let me see if I can get another question which has small fx. Because capital Fx we have dealt with it, we have seen that you have to differentiate. And now this one. Yeah, this one could be good because it involves sketching. Yeah, let's do this, okay. Though it is also capital Fx. Let me just see. But okay. Okay, since this one involves sketching, let's also try to do it. Let's also try to do this one. Let's try to do this item 3. Item 3. The good thing with this item 3, they already gave you the equations. They already gave you the equations. So we shall say a factory produces tiles during the firing process. I think you know that tiles to be manufactured, they have to be heated. I think that's what they mean by firing process. So a factory produces ceramic tiles, and during the firing process, small surface expansion defects may occur due to rapid temperature changes. Okay, the size of the defect measured in millimeters of expansion is modeled by a continuous random variable x. Okay, continuous. Do you see this word continuous? So we're dealing with, it is no longer discrete. It is continuous. That's one thing you should know. To understand and control the quality of tiles, engineers study probability distribution of the defect size. The cumulative, this word is key. It means that you are dealing with capital Fx. When you say the word cumulative, it means you're dealing with capital Fx. The cumulative distribution function of the defect size x is defined as, then bullet 1, for defect sizes less than or equal to 0. The cumulative probability is fx equal to 0. So this one is for x less or equal to 0. Okay. For defect sizes between 0 and 2. So between 0 and 2 is this. So this one is from 0. I think you know, under the bullets you saw that I wrote something, but I think I forgot to speak about it, but I wrote something here. If you look at that picture. In discrete, these two are not the same. But in continuous, I wrote that these two are the same. This is the same as this. So in continuous, these two inequality symbols mean the same thing. That is why here I don't mind. I can write this or I can write this. It is okay. I can also choose to write this. Reason I'm under continuous. Reason I'm dealing with continuous. So continuous, there's that freedom. There is that freedom. So here I can either choose to write this. I'm correct. I can either choose to write this. I'm correct. I can choose to write this. I'm correct. I can choose to write this. I'm correct. Reason continuous. Remember that. Reason continuous. Okay, let's go to the next bullet. The defect sizes between 2 and 3. The defect sizes between 2 and 3. The cumulative probability follows a model of this. So this one is from 2 to 3. Okay. Then for those greater than or equal to 3, so x greater than or equal to 3, this is the function. So the good thing here, they have already given us the functions What we need is to just get the value of the unknown, the value of the constant k. Okay, so where the constant k is unknown, and the engineers need to determine its correct value to ensure that the function represents a varied probability model. Varied probability model. Okay, using this information, answer the following questions. Part A, determine the value of the constant k that makes capital Fx a varied cumulative distribution function. Okay, I think let's begin with that. One, you must remember that capital Fx we don't integrate. Capital Fx we don't integrate. That should be in your mind. Capital Fx we don't integrate. What do we do? We simply substitute. Simply substitute. If you're dealing with capital Fx, don't tamper to integrate. So because this is capital Fx, I don't need to integrate to get the value of k. Remember in sorry. Remember when they gave you small fx and there was some constant, they could tell you that for you to get the constant, you integrate fx and equate to 1. Okay, that was for small fx. It is small fx where we integrate. For capital Fx, we never integrate. We simply substitute. Now, how are you going to substitute? There is something funny. Do you see this 3 and this 3? They can be got from any of these two. That 3 can be got. So when I substitute this 3 here, I'll get to 1. Okay. When I substitute this 3 here, I should get the same value. So it means that I can write that F3 will be equal to 1. Okay, and also be equal to k in brackets 6 times 3 minus 3 squared minus 6. So that is what I'm meaning by the word simply substitute. Simply substitute. Okay. So F3, it is here and it is also here. So I can write this to get the value of k, like that. So the same applies if I use this and this, but the problem with that, you know the problem with it? If I use this option of not 3 and 2, I can use this 2 here and this one here. Okay, but why didn't I use it? Because if I use it, the k which I want will vanish. Let's try. I'll get k over 2 times 2 squared equal to k in brackets 6 times 2 minus 2 squared minus 6. Do you see the funny thing? This k here and this k here will cancel. So in the end, I'll be doing no work. In the end, I'll be doing no work. That is why I didn't use this option, but it is also correct. I didn't use it, but it's also correct. So I chose this one because in this case, the k does not vanish. It remains, and I've got it. Okay, if there's any query you can ask. If there's any query you can ask. Yes?
Could you please repeat how we are saying that this?
How we are saying that?
1 which is equal to f of.
Okay. I've understood you. This is the reason. For something to be continuous, it means that where one stops is where the other starts from. Where one stops is where the other starts from. Now, for example, for this one, if I'm to sketch, I may sketch and it goes up to here. Okay, this is 1, this is 2. Now, for it to be continuous, where this one has stopped is where this other one should start from and proceed elsewhere, like that. Now, this value here, it means that when I use this function, I get this very point. When I also use this function, I get that very point. That is why we saw me that I could use this function To get the value of fx, to get the value of, okay, let me use the word y. To get the value of y when x is 3. I could also use this one to get the value of y when x is 3. I don't know if that is in in coordinate form. If this is x and this is y, and this one is a function, maybe y equal to a quarter x squared, maybe. This one is also another function, y equal to. To get this coordinate here, I could use any of these two functions, any of those two equations. If I use this one, I get the same value. If I use this, I get the same value. That is why you're seeing that here I used this first one, and also when I use this, I must get the same. Reason, continuous. Continuous means where one stops is where the other starts from. If that's not the case, then we should say it is discontinuous, meaning one can stop here, then another one starts from somewhere here. You see that this breakage, that means it is discontinuous. But ours, it is continuous. Where one stops is where the other starts from. I don't know, is it better now?
Yes.
Okay. Is there any other inquiry before I go to Roman next part of the task? Okay, now we can look at the next part of the task. It says, hence sketch the graph of fx. Hence sketch, what this? Yeah, the next part is to sketch. So now that we have the value of k, I can put it now where there is k, I'll put there the value of k now. K was 1 over 3. So put 1 over 3 here, you'll come up with 1 over 6 x squared. Put 1 over 3 here, you'll come up with this expression. Okay. Then I'll need to get I already know the value of f3 is 1. Okay, so f3 is 1, but I don't know the value of, and I don't know that the value of 0, f0 is 0, because they is the same as this. Do you see this? 0. And this 0, they must give the same value, which is that. Now this 2, I don't know it yet. That's why you saw me first get it here. So after getting it, I can now sketch my graph. Now I have coordinates. I have 0, when x is 0, fx is 0. Okay. Then I have when x is 2, fx is 2 over 3. Okay. Then I have when x is 3, fx is 1, like that. So that the ones I will use to draw. But remember, because there is a squared, it is no longer a straight line. Because it is squared, it is no longer a straight line. Now, how do we do? We use some knowledge of curve sketching. We don't need to go to the details of get turning points by differentiating and equating to 0 what. But from that knowledge of curve sketching, you must have realized that there is something called standard curves. If I give a curve like y equal to x squared, and I want you to sketch it, you don't need to go through all these ones. You need to know that it has a minimum turning point. If I give a value like y equal to negative x squared, you don't need to go through the details to get turning point. Just know that it has a maximum. Reason, the coefficient of x squared is negative. Here it had a minimum. Reason, the coefficient of x squared is positive. So that is the knowledge you're going to use in this case also. Because it is squared, it is a curve. But also because the coefficient of x squared is positive, it must be in this form. Okay. Then this one, the coefficient of x squared is negative. Then it must be in this form, like that. So that is the knowledge you're going to use to sketch. We don't need to go through the details of turning points. What we need to know what we call standard curves. With that understood, we can now come and sketch. I think the animation is not okay. Let me just do something small. Okay, so now we are good to go. So we shall need the values. Remember we said we have 0, 0, then you have 0 corresponding to 2 over 3, then you have 3 corresponding to 1. So from this to this, it is a positive coefficient. That is why it is in this shape. Half of it goes this, which is this, like that. Then from now here, from here, it is now a maximum. So half of it is in this shape. That's why you're seeing here a shape of that form to depict a maximum turning point. Then from there, beyond that, it is 1, but you don't know where it stops. That is why you put an arrow like that. Then also, there's something I didn't do here, but I encourage you are going to add it there because there's a year it disturbs students. Do you see here? Let's first go back to the cover and I see what I did and I show you. Do you see this one? You also don't know where these values end. All values less than 0 give 0 probability. So how do you show them on the graph? You must also show it on the graph by doing this, by putting an arrow. So here I didn't show it, but I want you to add it there on your graph. Draw something like this and put an arrow to show that for all values less than 0, they have 0 probability. They have 0 probability. Okay, and this is the question you can ask on the graph. If there's a question you can ask.
Teacher Ronald.
Okay.
Is it a must for is it a must for us to label like the curves, like the way I've done here, fx equal to?
Very must. It is a must. Actually, do you see this curve? However correct it is, if you don't label, you may put all these ones, but if you don't label, no mark. I think your teachers who taught you curve sketching must have emphasized that every curve you sketch should be labeled. Every curve you sketch must be labeled. So the same knowledge, we use it here. If you don't label, we don't know what the curve is about. We don't know what the curve is about. So make sure you label. Make sure you label. Any inquiry on the sketch?
Excuse me, teacher. The red arrow that you're drawn going this side is where I write fx is equal to 0.
Yeah, you're going to put fx equal to 0 because every curve you draw must be labeled. So this red line, I've told you that you include it there because in that year, it disturbs students. One mark was lost for not indicating that. Yet in the function you drew, you said x less than 0 and you gave it 0 fx. Now, why didn't you show it on the graph? That was the argument. So I also encourage you to add it there. Me, I didn't add it, but you add it there. You add it there. Okay. Hope it is better. Any inquiry? Okay, so the silence means, okay, yes. Vanessa, you can ask.
Teacher, is it a must to put an arrow?
It is a must. Do you know why? Because the inequality says x greater than 3. So you don't know where those values end. So you must put an arrow. Even here, the inequality is x less than 0. You don't know where those values end. So you must put an arrow to show that it is still continuing. It is still continuing. So it is a must. It is a must.
Okay, teacher.
Okay.
Thank you, teacher.
You're welcome. Any other inquiry? Okay, so that means we can go to the next part of the task. Next part says, okay, we have sketched. Now part B, find the probability density function of the defective size. Probability density function is small fx, meaning that we have to differentiate. We have to differentiate. Now, I want someone, I already shown you how to convert from small f, capital Fx, small fx. Now, I want someone to give me what I'm going to write on small fx using this capital Fx. Anyone to tell us what to write? Anyone? We want to get small fx from capital Fx. What should we do?
Shall we differentiate?
So give me what to write after differentiating. Remember, this was 1 over 6x squared, and this was 1 over 3 in brackets. So what are you going to write? The one who told us to differentiate. Okay, any other? It is true we differentiate. Now what are you going to write? In short,
A third x.
we write a third x. Then the interval will be
0 to x to 2.
Then the next part, this one, the k is a third. So what are you writing? You are still there? Okay, let me choose. Let me choose. I saw Janet. Where is she now? Yeah, she's there. Elsa Chirabo. Elsa, we are there. What I want is what to write when I differentiate this. Elsa, you are there? Yeah, I'm giving it to you. I don't want to give it to you. But
2x minus 2x out of 3. 2 minus x.
It is
2 minus 2x out of 3.
2 minus 2x out of 3.
Yeah,
Okay, how did you get it?
Oh, I don't know if it's right, but I multiplied the third by every component in the bracket, then differentiated them individually.
You said a third times. Okay, you said a third. So that gives you a third. A third times this gives you 2x. Then minus
2x
1 over 3x squared. I'm opening brackets, minus 2. Is that what you got?
Yes.
Then from there you say you differentiated to get
2x 2 minus 2x
minus 2x
out of 3.
Out of 3. Okay, hey, so that this division was not for all. It was for only 2x.
Yes.
Okay, then you are correct. Okay, I accept. So that means that we are going to come and differentiate. So differentiating, you can get that as your small fx. Okay, and there's an inquiry you can ask. Is it okay? Before we go to the next item.
Yes, teacher.
Okay. So now we have dealt with capital FX. I want to deal with a question which has small fx so that you can try out some questions. Let me see this one. Item 5. Should I do item 5? Okay, let's do item 5. Let me see item 5. Where is it? Item 5. Where is it? Item 5. Yeah. They want value of k expectation, then the probability. Okay. Let's try that.
Teacher,
I
have an inquiry before we move.
Okay.
So for me, I differentiated what was inside the bracket. So I got a third into 6 minus 2x.
A third into, that was, you got a third into 6 minus 2x. I think it is correct. Don't you say it here?
Oh, okay.
I only
Oh, yeah.
reduced it. It is okay. It is okay. So now we can try item 5. Item 5. Item 5 says it was from 2015. A telecommunications company is studying the signal delay experienced by data packets. These terms may be, I think those in ICT you study those words, data packets, bits, what. But if not, don't mind. What we only want to pick out the math in it. So through a newly installed fiber optic network, the delay measured in milliseconds is represented in a continuous random variable. So our interest as math is this word, continuous random. It is a continuous random variable. The only difference that now some of you are used to x. X is not the only variable they use. Actually, I can even use W. I can even use W. I can even use P like that. So here I chose to use Y. So when they change from X to another variable, another letter, don't think it is a strange question. Simply maintain the procedure. The answers will come out. Simply maintain the procedure. The answers will come out. Based on experimental data, the probability density function of the signal delay is modeled by the bullets 1 for delay values between 0 and k. The probability density function is this. So this one is for this inequality, y0 to k. I think most of you are used to constants being put in the function, but now this one is a little funny. The constant is in the interval, but don't worry, we shall see what to do. For all other values, the probability is 0. Now, all other is what brings in the word elsewhere. Elsewhere. For all other is what brings in the word elsewhere. So you can say, the constant k is unknown and must be determined so that the model represents a varied probability distribution. Okay. Then task, find the value of the constant k, find the expected signal delay, and find the probability that the signal delay lies between 1 millisecond and 1.5 millisecond. So the first thing to do is to write it in the format we know. I think in the format we know is this one. This is the format which is easy to work with. After that, we can now ask ourselves, how can we get the value of k? Because it is small fx, integration must come in. Because it is small fx, integration must come in. Remember, the first two items were dealt with, it was capital Fx. We didn't integrate anywhere. to get a constant. But here we must integrate. And we know that for constants, we get it by getting all y of fy dy equal to 1. Integrate all the values of y, it must be equal to 1. Total probability is always equal to 1. That is what we have to use. Only that here I did something funny. This shouldn't be the x. It was copy and paste. It should be the y. Because I'm going to integrate with respect to y. I'm going to integrate with respect to y. To substitute your fx, it is here. Then the limits are from 0 to k. Then I can integrate. Now, I want someone to give me the outcome after integrating. Anyone? When I integrate y plus 1, everything divided by 4, what do I get? Anyone? Yes?
Y squared out of 8 plus a quarter x.
Y squared over 8 plus a quarter x. Yeah, it is true. So what she has done, not x high. Did you say x also?
Sorry, y.
Yeah, that is now better. It should be y because we're dealing with respect to y. So it is correct. How did she do it? She said, let me first split the numerator and get y over 4 plus a quarter. Okay, now let me differentiate each. The y over 4 gives you y squared over 8. Then a quarter gives you a quarter y. So that's what she did. It is still okay. Another one can say, because this is a constant, let me first pull it out. And I write this, a quarter integral of y plus 1. It is also correct. Then when I integrate, this one is outside, so when I integrate, I'll come up with y squared over 2 plus y equal to 1. It is also okay. It is also okay. So like I've told you, this topic requires knowledge of differentiation and integration. Knowledge of differentiation and integration. Then I can substitute the limits. When I substitute the limits, I think now you realize that I only have one unknown, which is k. So I have to solve for k and be able to get it. It's a quadratic, meaning I can use the quadratic formula to get the value of k. So if there's a question you ask on that part A, but basically you should remember that small fx integrate, PDF, because now here now it is small y, fy. So small f integrate, capital F simply substitute, capital F simply substitute. Okay, now when I use the quadratic formula, this is what I'll come up with. So some choose to factorize. It is still okay. What you want is this method of showing how you got the values of k. Because it is true the calculator can also give you these values. But before you write them, how have you got them? So you either factorize or you quote the quadratic formula. Either factorize or you quote the quadratic formula. Then how do you eliminate? You realize that here the interval says from 0 up to k, meaning that this k must be a positive value. From 0, 0 is the smallest, and this is the maximum, so this value should be a positive value. In that case, k cannot be negative 4, therefore our k is 2, like that. Okay, if there's a question you ask on part A. Part B is expectation. I think we all know the formula for expectation. Our work is to integrate correctly. Now there. I want to integrate that. Anyone to take me through? I want to integrate this. Anyone to take us through how to do it? Anyone?
I think we get y cubed out of 8 plus y squared out of 4.
Y cubed out of 8 plus
Y squared out of 4.
Out of 4. Okay. How did it come about? What did you do first?
So I first integrated, like we integrated before in the previous step, and then
But now here there is a y, there is this y. What did you do with it?
I multiplied the numerators, both of them with the y.
To give you y squared over 4 and y over 4, like that? Is that what you did?
A question.
Okay. But I wanted the other one to first rectify because there's something fun in the integral. But okay, you can ask.
Oh, I was going to ask about her answer though.
Yeah, the answer has something missing. That's why I wanted that to find it out. It is true you expand. It is true you expand, but when you expand, you're going to get this, and this gives you y squared. This with this gives you y. Everything divided by 4, like that. So you can either choose to put the 4 outside, or you split the numerator, like we did. So if I choose to put the 4 outside, I'll get a quarter integral of y squared plus y, like that. Then I can integrate this one to give me y cubed over 3, okay, plus y squared over 2, like that. Then that will be better. That will be better. So in short, you can't integrate when there's a product of two functions. Each time you notice the product of two functions, you have to first expand, then you can integrate. First expand, then you can integrate. Then I can substitute limits and get the mean they wanted. Okay, is the integral now okay? The one I wanted to ask?
Yes, teacher.
Okay, that's good. Then the last part, it says the probability that the signal lies between 1 and 1.5. 1 and 1.5. And get that for us. What do we do? Anyone to take us through the answer for part C? Anyone take us through the answer for part C? What should we write?
We integrate the function with 1 as our lower limit and 1.5 as our upper limit.
You stay there. You're going to take us through that. So you said 1 as lower limit and
1.5 as the upper limit.
okay. Now when you integrate, what do we get? Let's just pull out a code.
Then we remain with y plus 1 dy.
Then when you integrate, y you get?
Y squared over 2.
Integrate 1.
Y.
Okay, then the limits are still 1 and 1.5. Then what do you do there after that?
You replace y with 1, so it becomes 1 out of 2 plus 1.
First, wait, replace y with 1. Remember, we begin with the upper limit.
Okay, with 1.5.
Yeah, that is better. Plus 1.5
squared.
Then after that, after upper limit?
Minus 1 over 2 plus close brackets again.
Yeah, so brackets should be used wisely. In math, brackets should be used wisely. Misusing them leads to loss of marks. So basically that was the answer. That's what they wanted. Because we're dealing with small fx, we integrated. Don't confuse these two. If it was capital Fx, we would just say f1.5 minus f1. But because it is small f, we have to integrate. Because it is small f, we have to integrate. Substitute limits and get the answer. Okay. So basically that is it. We have done 3 items. You can look for more items to attempt so that you can ask in the next lesson. That will be, I think, is it Thursday? So there's a question you ask before you call it a lesson. So Chomuhendo, is Patsy okay?
Yes, teacher.
Yvonne, Edith, is Patsy okay?
Yes, teacher.
Then Arnold, is Patsy okay?
Yes, teacher.
Okay, that's good. So I have not yet received papers for other schools apart from Gayaza. So I encourage you to send them so that we can see what we can pick out for others to also benefit. Otherwise, we can call it a lesson. Have a good day.
Thank you, teacher.
Thank you, teacher.
You're welcome.